All right, so moving on into the second part of problem number 9, it's the same setup, but now they're flipping things around. In part A, it was the volume that was fixed, and we were trying to minimize the surface area. Now in part B, the difference here is it's the surface area that's going to be fixed here at 20 square units, whatever units it is we're talking about, and we're now trying to maximize our volume. So what's that going to do for us? Step 1 is to state the parameter, the thing that can't be changed. Now it's the surface area, which was what we were trying to optimize, minimize in part A. That is now the parameter that has to be fixed. So our surface area, which is still going to follow the same formula of 2x squared, that's our bottom and our top put together, plus the four sides of the figure, the lateral faces, 4xy, and that has to be locked in at a grand total of 20. So we're going to need to solve that for either x or y, and I can tell you right now, solving that for x would be an absolute nightmare. We're going to be solving that one for y. In fact, let me go ahead and get on that right now. So we're going to get a 4xy is going to equal a 20 minus that 2x squared, and then we'll divide everything by the 4x here, and I'm going to make that, let's see, a y equals, so that's a 20 minus a 2x squared all over 4x. The only thing I could do to clean that up a little bit, although I don't think this is going to be very important, is divide a 2 out from everything. So that'll become a 10 minus x squared all over a 2x. So that's what y is going to equal. I'm going to go ahead and kind of circle that here temporarily. And now let's get ready to move on into step 2. And I think I need to slide this up a little bit. All right. So what we are trying to do here is trying to maximize the volume of this box. So the volume is what we're trying to optimize here in step 2. And our formula for volume, just like in part A, is the area of the base, which is x squared, multiplied by y. We need to use this substitution that we just came up with right here to put that in for y to get volume down to just an expression in terms of x. So it's going to be x squared, and instead of the y, we're going to replace all of that with, this is not very pleasant, 10 minus x squared all over a 2x. And I think distributing that x squared is definitely the way to go here. That would get us a 10x squared, a minus x to the fourth, all over a 2x. Now I'm looking at that expression right there. We definitely could do the derivative of that expression the way it's written, but it would require the quotient rule. What I think is a better idea is to split this thing up into two different fractions and simplify each one of them. And it looks like in both of those cases, the x on the bottom is going to cancel out. So this should work out nicer if I split it. The 10x squared divided by 2x is going to leave us with a 5x for the first term there, and then a minus. 1 divided by 2 is just going to be a 1/2. X to the fourth divided by x is going to be an x cubed. And that form of the volume expression right there looks like it's going to be the easiest version to differentiate. So let's move on into step 3 and take the derivative of that new volume equation we just came up with. Derivative of 5x is just going to be a 5, and the derivative of a minus 1/2 x cubed is going to be a minus 3/2 x squared. So there's our derivative. We'll set that equal to 0 and solve. So I'll bring that negative term to the right and get 5 is equal to now a positive 3/2 x squared. Let's multiply both sides by the reciprocal of the coefficient. That would be a 2/3. So I'll do that here and here if you need to see it right there. So the 5 times 2/3 is going to be 10/3. That equals x squared. And then we'll undo the square just by doing the square root on both sides. And we're going to get here, I'm going to jump up here, guys, and we're going to get x is equal to, it's the square root of 10/3. And I guess I gave you a decimal answer on the first part. So let's do the same thing here for part 2. All right, so what did I just say we were dealing with? It was the square root of 10 divided by 3 underneath that radical, and that's not what I wanted. Let's get that as a decimal. There you go, that's what we were looking for. Okay, 1.826 if we were going to round that to the nearest thousandth. So x is 1.826. 26. Now, just like in the first part, they're asking for the dimensions here. So we've given them what x is. We also need to give them the value of y. So to do that, ooh, this is a little ugly. I'm going to go back to this expression right over here and use last answer in my calculator to more accurately come up with what y can be. So 10 minus x squared over 2x. So I missed. All right, let's try this again. I'm going to do a stacked fraction right here, and it's going to be 10 minus my previous answer squared. So that was 10 minus x squared. All over it was a 2x, so that'll be a 2 answer right here. And that's going to give us an answer. Oh, maybe not surprisingly, again, the exact same value here for y that we came up with for x, 1.826. Now, again, step 4, guys, is to answer the question. Well, that's what they were looking for here, the dimensions. And so this is what we've come up with. And so in the first part of the problem, part A, what we realized here, guys, because the x and y values ended up being exactly the same, if you had a rectangular prism with a fixed volume and you were trying to minimize the surface area, a cube is the ideal way to do that. Now we've kind of learned right here in part B that if your surface area is fixed, if that's what you're limited by, and you want to maximize the volume of that box, a cube is the way to do that as well. So really what that kind of teaches us is that a cube is the ideal type of rectangular prism to get you the most volume and minimizing your surface area. That's really what that means. Now, of course, once we get outside the confines of a rectangular prism, there are other geometric solids that do an even better job of maximizing volume for a given surface area, but this is the best we can do if we're limited to working with a rectangular prism. So 2 different variations on that, but that's number 9.